We are talking about clustering or class-based models, specifically in the context of language, and specifically in the context of clustering words into categories. Of course, the principles hold in many other areas, but we're focusing on language. There are at least two different ways to look at it that I like to look at it, and one of it is through the lens of statistical estimation theory, and the other one is through the lens of information theory. So through the lens of statistical estimation, we're in the land of lots of categories, not enough data, high variance, and therefore we need to reduce the variance at the cost of increasing the bias. All right, so it's the famous bias-variance trade-off. And from that lens, any kind of clustering you do reduces variance, always goes in the same direction. Reduces variance, increases bias. We looked at many possible ways of doing clustering. You can cluster particular positions in the history. You can cluster more coarsely or less coarsely. So even if you focus on one particular position, you take a vocabulary of 100,000 words. If you cluster it down to 10,000, you reduce the variance, increase the bias. If you cluster it further to only 1,000 or 5,000 categories, then you further reduce the variance, increase the bias. You can cluster it into fewer and fewer categories, continuously reducing the variance, increasing the bias. In the extreme, you can cluster everything into a single category, which means you're no longer making distinctions based on what word it is, because they're all in the same category, right? So it's as if you eliminate that aspect of your history. So that's an extreme case of eliminating the variance completely for that position and increasing the bias. From the point of view of information theory, which is not very different, it's essentially the same thing, but I like to think about it as predicting a stream of events that comes at you can be done broken down into different parts. You can first predict that the next word is going to be a noun, and then condition on that, predict that it's going to be a singular noun, and condition on that, predict that it's going to be a concrete noun as opposed to an abstract noun, and then condition on that, you can say that it's going to be furniture, and condition on that, you can say it's going to be a chair. So that's basically the chain rule in probability. And you can think of different ways of breaking things down. One extreme way we saw earlier is if you put all the words in the vocabulary into a tree and you label the different children in each node, the binary tree, different children with 0 and 1, you can represent every word as a string of bits, and you can predict one bit at a time. And that sort of brings you closer and closer to what that word is. I want to focus on one particular class-based model, and that's a simple class-based bigram model. But everything we say applies to more complicated models. The graph that goes with it is this one. Etc. There could be other graphs, but that's what I want to work with. That's the simplest one. And I'd like you to be able to go back and forth from what's called a factoring of the probability distribution to a graph, and back from graph to factorization. So the factorization here would be probability of word I, given the word in position I minus 1, is going to be factored as probability of class I condition on the class of the previous word times the probability of word I given class I. Now I can multiply things of this form for I goes from 1 to n and get the likelihood of the entire corpus according to the model. Or I can work directly in log likelihood, and that means take the log of this, and this becomes a sum. So the log likelihood of the data given the model is a sum of the log likelihood of pi given pi minus 1, where I goes from 1 to n with some suitable initial boundary conditions. And that becomes sum of log of p of ci given c of I minus 1. I use the letter C interchangeably as the class, like Ci is the class of word I, or sometimes I say C of something, so that's a function that takes the word and tells you what the class is. But you know what it means. So Ci is C of Wi. And I choose to write it down separately. I'll write, so it's the log of this plus the log of this. But I'll write them down separately, just not to confuse things. I'll put the W here. Plus the same sum of log of P of Wi given Ci. So I can take what happens in every step of the generation, factor it based on my assumption of how things factor, that graph. If the graph were different, if it, for example, it had these connections, then the factoring would look different. If it had these connections, factoring would look different. It wouldn't be a bigram. But I'm making the simplest assumption I can think of, and therefore I have only two factors, and I'm collecting them separately. I also want to mention that I'm making here the assumption of hard classes. To remind you, a hard class is a partitioning of the vocabulary such that every word belongs to one particular class. And I know how my classes are defined, so given a word, I know exactly what class it belongs to. This is not the case for parts of speech. Part of speech is an example of what I call soft clustering and overlapping clusters, where given a word like saw, I don't know necessarily if it's used as a noun or as a verb. But I'm talking here only about hard classes. I will soon talk a little bit about soft classes. So in hard classes, you have a vocabulary, and it's broken down into non-overlapping classes. It's called a partition. These are equivalence classes. So under this condition, the log likelihood of data given the model is broken down into these two parts. Now I can look at these two parts. I can associate them with this transition versus this transition, right? And I can also say that if I had the best possible model, if my model was estimated perfectly, then this, let me take the average log likelihood. Average log likelihood, that means I divide here by n. So I divide here by n and here by n. I can kind of look at this quantity, the average log likelihood of predicting this transition, and I can think of it as the conditional entropy of C in position I, condition on C in position I minus 1. Kind of. I say kind of because entropy and conditional entropy are defined relative to particular distributions. The distribution that I'm defining it here relative to is actually the empirical distribution of the training data. Right? Not necessarily the true distribution. And if I wanted to be really, really rigorous, there is the true distribution that I don't know, there's my model distribution, which is my smooth estimation, and there's the unsmooth estimation, which is the empirical distribution of my sample, of my training data. So don't hold this to a mathematical rigor. I'm just trying to create intuition. If you think about the distribution of the training data only, so that's an empirical distribution. It means that the signs, it's the relative frequency, unsmooth relative frequency distribution. Then under this distribution, and assuming I didn't do any smoothing here either, this corresponds to the entropy of this transition, the amount of uncertainty that I have in predicting the next class from the previous class, the average amount of uncertainty that I have. Similarly, this corresponds to the entropy, under the same kind of quotes, entropy of predicting word given a class. So it's word I given class I. So I can, from an information theory point of view, I can kind of separate it into two processes and maybe put two teams to work on separately in parallel on the two processes. One specializing in predicting how classes follow other classes, and the other specializing in predicting how word comes out of a class. I can measure the number of bits that represent each one of these two processes. That's my entropy. And they're additive. This is a very convenient way to look at it because you can now do arithmetic. You can do manipulations with these quantities. For example, you can say that this is equal to the entropy of word distribution minus the mutual information between the word event and the class event. Right? Now I'm manipulating information theory quantities. Similarly, this is equal to the entropy of the class distribution minus the mutual information between two successive Ci minus 1 and Ci. Two successive classes. I can easily estimate this. This is just a unigram distribution over my corpus. I mean, I estimated from the unigram distribution over my corpus. What do you think this is? It's the average amount of information that knowing the word gives you about the class, or that knowing the class gives you about the word. What do you think about that?
How informative your particular partition is?
Right, but suppose I know the word. How much uncertainty is left about the class? Did I hear an answer? 0. It's a hard clustering. You know the word, you know the class. So knowing the word gives you everything you need to know about the class. In other words, this is equal to the entropy of the class. Because once you know it, the remaining entropy in the class is 0. So now I put them together, and the average log likelihood of the data according to my binary class model is, I put the wiggle here, not because it's approximate, but because I'm not defining exactly. Well, I'll say it's exactly as long as you understand that this is with regard to the empirical distribution. All these are with regard to the empirical distribution. Does everybody understand what I mean by the empirical distribution? I mean, taking the training data and pretend that it's not a sample, pretend that it is the distribution. So if something occurred once in the training data, the empirical distribution says it has a probability of 1 over n. If something occurred 7 times, the empirical distribution says it has a probability of 7 over n, and so forth. So I'll call that empirical distribution, I'll put the d here. So everything is under d, then I don't need the quotes. This is now correct. Also assuming that this log, this probability also comes from the empirical distribution. Now I'm rigorous. All right, so now I write them together. This part is h d of c minus I of ci minus 1 ci. And this part is h under d of w minus Something should cancel here.
So the H of C is H of W, right?
H of C is not H of W.
Yeah, because there is.
They're independent, so information of W and C should be entropy of W too.
Information of W and C should be, no, it's not entropy of W also. W has more entropy. This is W. I'm sorry, this is not like this. This is subset. This is C. The information in C is a subset of the information in W in the sense that if you know the class for sure, you don't know the word. If you know the word, you know the class. There is more entropy in knowing the word than in knowing the class. So knowing the class is a subset of knowing the word. The mutual information is their overlap. So H of C given W is 0. H of W given C is not 0, is greater than 0. Okay? One is a subset of the other. You found my mistake?
It's because the log likelihood is the minus entropy.
Ah, thank you. Okay. So where did I... so average log likelihood. So shall I say let's take the negative average log likelihood?
Yeah.
Okay. Negative average log likelihood is the thing that's related to entropy, because entropy is log of 1 over p, not log of p. Thank you. So this is negative here and negative here. It still doesn't explain. Let me write it from scratch. So negative average log likelihood of my data given my model is, I'll start there, the entropy of the word according to the empirical distribution minus the mutual information between, minus mutual information between word and entropy, which is the entropy of the class, plus entropy of the class minus mutual information between two successive class variables. Okay? And now we see that these two cancel. So what it tells me is that when I choose a clustering and I build my model based on the clustering, the negative average log likelihood of the data according to the model will depend on the mutual information between successive tokens, token classes. This part does not change as you change the clustering, because it depends only on the word. It's fixed. You calculate it once from your training data and it's fixed. This part, as you change your clustering, can change, and therefore the negative average log likelihood would change. Now if you want to use a criterion of maximizing the likelihood of your data, right, the maximum likelihood criterion, so the clustering that is the winner, I like to use stars for winners, is the one that maximizes the average log likelihood of the data and therefore minimizes the negative average log likelihood of the data. So it will be argmin over all possible clustering of this plus this. This minus this. Right? Argmin, but this doesn't change by the clustering. So we're left argmin of negative mutual information between Ci minus 1 and Ci. Now I'm going to change again the min to a max and get rid of this negative sign. So I'll make this max. And this is my criterion. The maximum likelihood training of clusters for this particular type of model, the simple bigram class model, effectively what it tries to do is to find clustering, a particular fixed hard clustering, a particular partition of the vocabulary, such that the mutual information between the class of two successive words is maximized. Can you tell me what the solution to this would be? What would be the best clustering to achieve this?
I have a question.
Clarification?
Yeah, sorry.
All right, go ahead.
The fact that you are assuming the entropy under the empirical distribution, does
Mhm.
this reflect the fact that your clustering, the final clustering that you get is optimal, or it may not be optimal?
No, it may not be optimal at all. In fact, I'm getting at that point. There is a very simple solution to this. If you just spend enough time thinking about under what conditions, under which clustering is this maximized, based on the empirical distribution. Do you think the mutual information between successive classes would be higher when you have more classes or higher when you have fewer classes? Fewer. Why? Okay, well, let's take it to an extreme. Suppose there's a single class only. So all the words fit in the same class. So what is the amount of mutual information between the class of the previous word and the class of the next word? 0. There's no uncertainty in the class stream at all. It's always the same class. Suppose now there are only 2 classes. And let's assume for simplicity that they are equally frequent. How much information does knowing that the current word is in the first class tell you about the class of the next word? At most 1 bit. At most, because that's the most amount of uncertainty you have in that second word. Suppose now you had not 2 classes, but 100,000 classes. In other words, every word is in its own class. Now you have more information. You can get the maximum here simply by keeping every word in its own class.
Which then eliminates the fact that you are actually using class-based models.
Right. And this goes back to your question. If I lived in a world where the true distribution was the empirical distribution, I should not use classes, because I'm throwing away information, I'm throwing away distinctions. That ties into the statistical way of looking at things that says that if you didn't worry about the variance, namely about the fact that your data is just a sample from the truth and not the real truth, then you should not introduce any bias. Remember that classes always use bias. They always chop things. They make them more simple, less detailed than they really are, because they're starving for data and they're trying to pull together data. If you live in a world where the empirical distribution is the correct distribution, you should not do that. For the same reason that if you lived in that world, you should not use a bigram. Trigram is better. 4-gram is even better than that. 10-gram is even better than that, right? You should not chop off your history at all. But of course, we don't live in that world. And the problem of using this criterion is that it will push us towards keeping maximum information, no bias, but it will fail miserably on new data because of the variance problem, because the data is just a sample from reality. So what we're going to do is know that we do need clustering, that it does reduce variance, but we're going to cluster things and under a particular assumption of the number of clusters, try to minimize the bias, namely minimize the negative average log likelihood. So I'm going to choose in advance how many clusters I'm going to have, and then saying, given that I'm shooting for 1,000 clusters, under that condition, what is the best way of clustering the words? If I did not restrict in advance the number of classes, this criterion will push me towards having 100,000 classes, each one of them separate word. So the solution to this is 100,000 classes. I'm going to change my solution. I'm going to change it to such that number of classes, I don't know how to write that. Number of classes, no, just write number of classes is some fixed number k. That number, if the vocabulary is 100,000, k could be lots of things. It could be 10, just 10 classes. It could be 1,000 classes. It could be 10,000 classes. It could really be in the whole range. The one that's closest to not making a clustering decision is the one that has many, many classes. I only put together a handful of words at a time. All the names of days of the week, all the names of colors, all the names of cities go together. It's very easy to make these very reasonable classes that consist of small groups. In the other extreme, if I go to here, I'm making very, very broad classes. Abstract nouns, transitive verbs, names, prepositions, and so forth. That would correspond to a very, very strong reduction in variance at the cost of introducing much more significant bias. So this is the less detailed model. This is the more detailed direction. And this is the more robust. More robust means low variance, and more detailed means less bias. Okay, so now suppose I fixed k at some value, let's say 1,000. I now have a job of trying to partition the vocabulary of 100,000 words into 1,000 clusters. Each one would have, on average, 100 words. It could vary. How many ways are there of doing that? How many different ways are there of clustering 100,000 words into 1,000 classes? It's actually more than that, but it's on the order of something like that. So that's a problem in combinatorics. So let's say you can assign them each to you have 100,000. Each one you have to choose what class to put it in. So that's 1,000 possible classes raised to the power of 100,000 times, right? And then you have to take into account that two clusterings that are the same except by permutation of the numbering of the clusters should be considered the same, and there are 1,000 factorial permutations. So that's a number, unless I got it wrong. It's huge. Okay, we can't get there. We can't even begin to get there. So even though we defined a very well-defined criterion, and even though for any particular clustering we can calculate this number, and in the paper you have the exact formula of how to calculate this number, but it's if you follow your notes on information theory, you can derive this right away because this is based on the empirical distribution. So you collect. All you have to do is collect the counts of all the words and the counts of all the. In fact, for any particular clustering, you only need to know the counts of the classes, of the particular classes, of the class bigrams and class unigrams. And you can calculate the entropy of the class distribution minus the entropy of the class distribution given the class before it. It's the same thing. So we can calculate it relatively fast for any particular clustering. But there are so many possible clusterings that to truly optimize this is hopeless. So we're going to use heuristic. We're going to use a greedy method. The greedy method would consider a variety of clusterings. It can even consider millions of them. Remember that each particular clustering takes us a reasonably small amount of time to calculate this number. And we're just going to search for a clustering, search in a very large space for a clustering that gives us as large a number here as possible. There are two general types of algorithms for doing that. One of them is top-down, the other one is bottom-up. Top-down is called top-down clustering. Bottom-up is called bottom-up clustering or bottom-up agglomerative clustering, because you gradually agglomerate the classes into fewer and fewer. And we should think about them. They're not symmetric. They have advantages and disadvantages. So what would the top-down clustering do? They're both heuristic. They're both greedy. They're both imperfect and still computationally quite expensive. The top-down would start with the entire vocabulary as if it belonged to one class and would try to first form one partition into two sets such that we have two classes. And as you know, just this question has 2 to the 100,000 answers. How many ways are there of breaking the whole vocabulary into two sets? 2 to the 100,000. So I'm not going to even be able to examine all of them. But I'm going to heuristically try to break them down in a way that makes sense. Makes sense means has a high mutual information between the two classes. So suppose I broke them down in one particular way. I now map all of my words in my training data into these two classes. And my corpus, my training corpus, becomes just a long, long string of n tokens. Each one is either A or B. Class 1, class 2. It's like result of flipping a coin. And I can easily calculate the mutual information between knowing the value of one and knowing the uncertainty and the value of the next. Once I find a solution that I think is reasonable, I'm not going to find the optimal one, but I'll find a reasonable one. I'm going to now recursively apply the same step to each one of the two parts. I'm going to try to break this into two and this into two. And then break them this way and so forth. That's top-down clustering. Every time I make a decision on how to split them, I'm going to heuristically try to find a way of putting some of the words on one side, some of them on the other side. You could use your linguistic knowledge at the very, very top to decide, let's put all nouns here and all verbs here, and then you have to decide where to put adjectives and adverbs. You can also jump ahead and say, let's start with 7 categories, parts of speech or whatever. Keep in mind that parts of speech are soft clusters, so this is not that good of a distinction. But you can assign each word deterministically to the part of speech that is most common for that word. The second method is bottom-up, also known as agglomerative. Clustering. This is top-down clustering. In bottom-up clustering, you start with every word in its own cluster. So you have word 1, word 2, all the way to word 100,000. You have 100,000 words, 100,000 clusters. And now the step you're looking for is the step of merging 2 of the existing clusters into a single cluster. Suppose you merged some word wi from the vocabulary with another word wj. You combine them together into a joint cluster that has word I and word j in it. You've now reduced the number of clusters from 10 to the 5 to 10 to the 5 minus 1. Just tiny amount. Whenever you reduce the number of clusters, whenever you merge, you actually make this number worse. Remember that if there was no restriction on the number of clusters, the maximum value here would be when every word is in its own cluster. So you're starting with a situation when this mutual information is at its highest possible value. But now if you force the system to do a clustering, it should choose the merge that makes this worse by the smallest amount possible, that reduces it by the smallest amount possible. So every two words that you consider merging, calculate what impact it has on this. The impact would always be bad. They always make it worse, but try to find the one that makes it worse by the smallest amount. How many things do you need to consider? How many pairs are there? 10 to the 5, choose 2, right? That's still a very large number. But it's much smaller than the number you have to consider here, which is 2 to 10 to the 5. Much, much smaller. So you're searching a much smaller space here. So it is easier to optimize this merging step than a splitting step. Now, 10 to the 5 choose 2 is about 10 to the 10, right? It's half times 10 to the 10. You can actually do that. If you're very, very quick about it, if you have clever data structures, you can imagine running an algorithm 10 to the 10 times. Or don't start with a 100,000 vocabulary, start with a 10,000 vocabulary. We can talk about shortcuts of what you can do. But this is borderline doable. This is nowhere near anywhere doable in anybody's dream. After you merge this, you have 10 to the 5 minus 1. Now you apply the same algorithm again, considering the 99,999 different clusters, which happen to have one word in each cluster, and then one cluster has two words. But you apply it again, and again you do about this much, this many attempts. And again you merge, and again you're going to lose something on the mutual information, but you try to lose as least as possible. And you keep doing that, and you form a pyramid here. Somewhere up the pyramid, you're down to a fairly large categories, and there are fewer of them. Let's say they are C categories. One through C. Each one of them has a large number of words. On average, 100,000 divided by C. So this is C now. And now you're considering all ways of combining two of them into one. Now there are only C choose 2 ways of doing it. If C is 2,000, that's 2,000 choose 2. That's totally doable. That's 4 million. Or 2 million. So as you go up the pyramid towards the top, it becomes easier and easier. And you can actually do it exhaustively, maybe, depending on the size of vocabulary and the size of your computer. But you can imagine doing this process exhaustively. If you did manage to do it exhaustively, suppose you didn't start with a vocabulary of 100,000 but only 10,000, and you have a very, very fast computer, did you get the optimal answer to this problem? Did you solve it exactly? No, why not? Because it's greedy. Each step was optimal, but it doesn't mean that the whole process was optimal. It's possible that if you did a step here that was not the optimal one, you would later be able to do a better job. So being able to do it exhaustively still does not mean that you have the absolute best solution. Whereas here, it's even more hopeless, because even the first step here is far from optimal. And Once you made that first division, you're not going to overcome it, except you could do something to try to overcome it. I'll tell you in a minute. We're going to stick with this method. And in fact, the paper that I asked you to read is by the IBM group, and they use this method. The Philips group, I think, were the first group to do the top-down. And there were people who came after that who did a variety of top-down and bottom-up clusterings. But this is, I think, the most famous one. Mutual information between successive classes, class I minus 1, class I, gets worse. Worse. By worse, I mean smaller. As you go up here. It gets better as you go down here. All right. This is still way too much. So there are a few shortcuts that you can introduce. Let's do it in terms of size of the vocabulary. So at the bottom of the pyramid, it takes V choose 2 comparisons, which is order V squared. Right? How many merge steps are there if you want to build the entire tree? Hello? Size of the vocabulary, thank you. V steps until you get to one class that includes everything. So you have V square comparisons in every step to choose the best one. And you have V steps here until the complete merge. It's true that as you get to here, the number of comparisons is significantly smaller. But from the point of view of asymptotic dependence on V, it doesn't matter. It's dominated by what happens at the bottom. So it's like the area of a triangle is the base times the height divided by 2. But that divide by 2 doesn't matter asymptotically. So we have 2 factors of V here. We have 1 factor of V here. Now you have to ask yourself, how long does it take you to calculate this value for each particular merge suggestion? And the answer is the sort of straightforward way of doing it takes V squared, or rather C squared, the number of clusters squared, because you need to look at the effect of the merge on every combination of Ci minus 1 and Ci. And C, in the worst situation at the bottom, is very close to V. So this introduces another factor of V squared. Order of C squared or V squared for each comparison, for each calculation of I of Ci minus 1 Ci. Not for this. We're forgetting about this now. It's all for the bottom up. So we have V iterations of clustering, V steps of clustering, each one looking at every pair, which is on the order of V squared, each one taking on the order of V squared. So you get V to the 5, which is way too much. Now we're talking algorithmics. Now we're just talking about how do you solve that problem. So it turns out you can actually reduce it considerably. The cleverest trick they used was they were able to reduce the amount of work it takes to calculate this to actually constant. And the reason they were able to reduce it to constant is because they didn't recalculate from scratch. They undid the effect of one merge and put in the effect of the other merge. So it was just 2 steps. Read the paper for details. But basically, they were able to get rid of this. So they're down to V cubed. V cubed is still a lot, especially that the paper was written almost 20 years ago, and computers were even less than they are now. So the way they solved the V cubed problem is they made V no more than 5,000. So this is 125 billion doable with a lot of computers. Today, we could do what they did with 10,000, maybe even more. So what they figured they would do is they would cluster the 5,000 most common words in the vocabulary, and then later they'll throw in the less common ones heuristically to whichever cluster they belong better to. Belong better to as in calculate something similar to this. Another thing they did was they realized the process is greedy, so it's not optimal. So they allowed local optimization, or local, some kind you can think of it as gradient descent to improve the result. So they somehow got to say 2,000 clusters, and now they said, is there any word in this cluster that if I move it to this cluster, it would improve my measure? Remember, they can calculate that measure in constant time. So they actually took every word in every cluster, one at a time, and checked to see whether moving it to any one of the other clusters would improve the mutual information. There are only V words in all of these together. And there are only C clusters. So this was a step of V times C, which is nothing, right? V squared is nothing relative to V cubed. So it was a small part. So every now and then, words would migrate from one cluster to another. And when they finished migrating, then they do the next step of agglomerative clustering, looking for one more merge of two clusters. And then again, based on the new situation, try to see if moving one word at a time would improve the situation. You can think of other heuristics. But the idea is you're searching a huge space, you're searching it heuristically, greedily, you're trying all sorts of things. The not so nice thing about allowing words to migrate is that you end up with a mess, because a word that started here and went up the tree to here, all of a sudden gets transferred to here. So you don't have a nice path. If you did not allow this lateral migration, you get a very nice tree of the type that I discovered or discussed on Monday, where words are merged as pairs, and that defines for you a whole tree, binary tree of words. I want to show you some snippets from their from the tree that they created. It does make a lot of sense. The order of the words?
Yeah.
No. Clusters are clusters, they're sets. The order of the words within a cluster does not matter.
Now we're shifting them to different clusters. Like not in the words.
The order in which you consider moving them? Is that what you meant? Yes. Yes, it does matter. You're right.
So
You're right.
They,
I think randomly, arbitrarily. Yeah, it's a search. It's a heuristic search. You're right there. That's a good point. No, I want to do this. I want to. So obviously I can't show you the whole tree, but I can show you little snippets from the tree. It looks pretty good, doesn't it? It's really neat that this process came up with these beautiful, linguistically consistent, coherent snippets. Look how quarter and half are siblings, and they're first order cousins of month, and then of week and day and year and day. Isn't it beautiful? I mean, I think this is really, yes?
Yeah, I actually have a question. So, like, far as I understand, the original algorithm where you can joining one word at a time, but you can also like merge like clusters together. And actually, in this picture, it looks like it's not always one word at a time.
No, the algorithm does not merge one word at a time. The algorithm, in its most general description, merges two clusters into one merge of a cluster at a time. But we start it with every word being in its own cluster.
Right.
So the very first merge is of a cluster of a single word with a cluster of a single word. The next merge might be of a cluster of a single word with a cluster of a single word, or a cluster of a single word with that cluster of two words that we merged before.
Then we'll have fewer steps than order of key. Because you can, if you always merge in pairs, you can first make pairs, then pairs of pairs.
Right, but every merge reduces the number of clusters by one. Right? You could do them in parallel, you're right. You could represent it by a tree with less depth because you're merging things in parallel. But that's not what they did. Sequentially, they merged one pair, then considered that new result a v minus 1 clusters, and then did it again. Every merge takes two clusters, converts it into one, reduces the number of clusters by one, and therefore if you start with v and end with 1, you did v minus 1 merges. My point here is that it does do a very nice job. Of course, you have to realize that they chose very neat snippets and that they don't all look like that. And in fact, you cannot take the vocabulary and even manually create such a beautiful thing that's always going to be beautiful. However, it does a nice job. They then stopped at about 1,000 clusters and used that particular partitioning as their bigram-based model, class-based model. They also took the words outside the first 5,000 and threw them into whichever cluster they fit best into based on the mutual information criterion. And then they show you some examples of the clusters they ended up with. Which example do I want to show you next? All right. These are randomly selected word classes. So these are not really the best clusters they had. They're randomly selected. Can you see it, or should you want me to zoom in more? You can see it. Okay. Unlike the example with the tree, where the example with the tree consisted of the 5,000 most common words, so each word was a nice, neat word. Here you see the vagaries of real work with language models. You have all sorts of garbage words, words with misspellings, words with uppercase, lowercase, hash signs, whatever. Still, the classes look very nice. Look at the one below the number 3. Running, moving, playing, setting, holding, carrying, passing, cutting, driving, fighting. It's, you know, it's not just a verb. It's not just in the gerund. Is that what it's called? You linguists, what do you call the ing thing? Gerunds. Gerunds, thank you. It's not just gerund verbs. It's also a particular kind of verb. And it all came out of just information about which word was before you and after you, right? It's all based on mutual information between successive words, specifically between classes of successive words. So it's very neat that you're able to come up with these classes. But you also see some weird poop. Annual, regular, monthly, daily, weekly, quarterly, periodic, good, and convertible. And you look at it and you say, okay, giving them a break. I mean, it's a beautiful technique. They didn't use any linguistic prior knowledge. It's all data-driven. It's 95% good, right? What else can you ask for? Well, when they plug this model into a real-world new test set, it didn't do better than the standard word bigram. And even when they interpolated it with the standard bigram, which is what you should always do when you fail, it still didn't do better. Okay? Why? It's so beautiful. I don't think that's the reason. I think you can control the number of classes so you don't overfit. I think the answer, that's my answer, You may disagree. My answer is that it's the phenomena I mentioned to you before, and that is that the words that clustered very well, the ones that impress us here, are the ones that occurred quite a few times. But words that occurred quite a few times are very well estimated. They don't need help clustering. It's the words that occurred few times, like convertible, that needed help clustering. But because they occurred few times, they did not necessarily get clustered reliably into the right place. Maybe you as a linguist would take the word convertible and look for a class of, coupe and jeep and whatever. But the algorithm wasn't able to do that. So my personal conclusion is that clustering using the same data that you use for training a model doesn't buy you anything by itself, because you're trying to get something out of nothing. You don't have enough information about rare words, so you're using the information you have to decide where to put them. If you are able to bring in some other information, then you might get some value out of it. For example, if you impose some linguistic constraints, you pre-classify each word by what type of word, what semantic categories, or you look in the dictionary, what have you. If you can bring in some other information, then you might be able to do something good with it. If you're able to cluster them based on a much, much larger corpus that for some reason is not available for building your final model, that's useful too. If you believe that these classes have existence outside your particular corpus, for example, in other domains. If you can bring to bear parallel data from other corpora, so that you cannot directly train models, but you can suggest which words are similar based on in other languages. For example, words that have the same translation into another language, they're both translated in the same word. Sometimes they're similar words. I don't know. Maybe, maybe not. But just the pure vanilla approach of use the data to make clustering decisions and then use the clusters to build models is not going to help. That's my personal belief. Nonetheless, the method of clustering based on mutual information is very general and very powerful and very impressive. And by changing the model that you start with, or the criterion, but still keeping in mind information theory and keep in mind the notion of mutual information, you can change the kind of clustering you get. For example, the clusterings we get here are what I would call syntactic clustering. Syntactic clustering is words fall into the same cluster if they can be exchanged from one another without ruining the syntax, although they might change the semantics completely. So anywhere that you can fit the word, where is the quarter? Oh, it's not there. I'm sorry? Annual. Everywhere you can put the word annual, you can probably put monthly, daily, and weekly. Annual meeting, monthly meeting. Annual report, quarterly report. Okay? Even court, judge, and jury, notice that all of these are nouns, singular nouns. Not only are they from the area of law, but they're singular nouns, so they fit well syntactically. They may vary semantically. Suppose you want a different kind of clustering. Suppose you want to cluster words based on their semantics. Namely, you want to put together the words bank, banker, bankers, banking, banked, treasury, interest, bill, account. No, I'm only using nouns here. Buy, sell, exchange, verbs, nouns, adjectives, yield, yielding, yielded. You don't care about the syntactic similarity. You don't want them to be syntactically possible necessarily to take one put the other, but they want them to be all about the same topic. You can use the same ideas from information theory. You just define your measure of information differently. For example, you can say, let's look at neighborhoods of 10 words or a sentence, and let's see what words tend to occur in a sentence. So let's take the example of a sentence. Let's look at our training data as a set of sentences and ask ourselves, if I know that the word bank occurred in a particular sentence, or that it didn't occur, if I'm told whether it occurred or didn't occur, like humidity and temperature, which other word does it give me the most information about? So you can look at the mutual information between knowing whether a particular word occurred and knowing whether another particular word occurred, right? So that would also be mutual information, but it's not based on adjacency. It's based on co-occurrence within the same sentence. It's the same concept of mutual information, just the events, the random variables, are defined differently. Let's spell that out in a little more detail. You have a set of sentences, S1, S2, S3, Sm, and you have the event bank, which is 1 if the word bank occurred in a particular sentence and 0 otherwise. So it's a random variable, a binary random variable, 0, 1. And you have another word, money. So you create another random variable, and again it's 1 or 0 whether that word occurred in a sentence or not. And now you have a joint distribution of these two random variables. Not only do you know the entropy of bank, entropy of the event bank is in a sentence, and the entropy of the word money in a sentence. So bank or money being a sentence is basically a random variable. Sometimes it's 0, sometimes it's 1, if you choose randomly sentences. But you also know the joint distribution in your corpus. So you can calculate the joint entropy, you can calculate the conditional entropy, you can calculate the mutual information. They're all kind of the same thing. And you can look for pairs of words that have maximum mutual information. You can fix one word like bank and say, find me one other word that has the most mutual information with this one. Or you can just say, give me the two that have the highest mutual information. And you can use that as a basis for clustering. When you do that, here's an example of what they found, what they got. They call these semantic clusters for obvious reasons. So now they have at the top, we, our, us, ourselves, ours. That's nice. But the second one, questions, singular and plural, you would often not get it in the syntactic clusters because many times you need a particular singular or plural. Asking, answer, answers, answering. Exactly what we wanted. Right? Many different parts of speech, but the same root. Yes?
By this technique, you would also tend to throw up collocations which are two words essentially, which don't necessarily mean the same thing, but they go very well
Right.
together.
Right. Yes, you would capture that. So they call it semantic clusters, but it's not really that they all have the same semantics, as they tend to co-occur. It's a collocation statistic.
Isn't this again heavily dependent on counts? Like
Yes.
how many times do you observe a particular word?
Yes. The mutual information between the two random variables I talk about would be strongly dependent on counts. By the way, I want to make sure I discuss something at some point, so let me just tell you it and don't let me get away without it. There's a big difference between mutual information between two events and correlations between two events. Remind me to discuss this at some point. They're very different. They both capture the connectedness or the relationship, or they're both called measures of association between two variables. But they're different, and there are actually many other measures of association. They each have their own properties. But very commonly used ones are correlation and mutual information, and we need to understand the intuition of when to apply which. Okay, so these are semantic classes. You can also look at something they called sticky pairs. Sticky pairs are pairs of words that tend to occur a lot together, such that they provide the most mutual information. This is more related to the syntactic clustering before, based on the bigram. But instead of trying to create classes out of the vocabulary, it's just looking at the two words, pairs of words that are the most informative of one another, such that when you see the first one, you're almost sure that the next one is going to be it. And they actually ranked it by number of bits of mutual information that you got. And not surprisingly, the first pair is Humpty Dumpty. Because when you see Humpty, you always see Dumpty after that. So you basically reduce the entropy of the next word to 0. So you see here that it's, oh, you don't see it there. You see that 22.5 bits basically says that the original entropy of a word was 22.5 bits, because when you see Humpty, it's down to 0. maybe almost 0. And you see there's quite a few pairs that are very close to this. So Klux followed by Klan, and Ku Klux, Ku followed by Klux, and I don't know what Cha Nult is. Lao Bao, Nu Chan. So these are probably names of cities, maybe in Vietnam. Any Vietnamese here?
No, it's not Vietnam.
Not Vietnam. So in China?
No.
Laos? What is it? Nobody knows?
Which one?
Cha Nult, Lao Bao, Nu Cha, Zedong is Mao Zedong.
Yeah.
Yeah. Avant-garde, Taj Mahal.
Gizzard Shad, something that just occurred once.
Which one?
Gizzard Shad.
I doubt that it occurred once because they probably threw away things that occurred fewer than a certain number of times. I'm almost sure of that. But if there was a single article and it occurred 10 times there, but gizzard never occurred by itself and shad never occurred by itself, they will have. So it comes to the issue of, are these reliable estimates of true mutual information, right? Because if you have a finite number of counts and it's just a coincidence, it could be. They weren't looking for, getting the correct number. They were looking for finding interesting top matches. Abu Dhabi at the bottom too. The take-home message is that mutual information is a very useful measure for bringing up, events that are strongly related to one another, that tell you things about one another, and it's a good way of suggesting to cluster them together, either for semantic clustering or syntactic clustering, for creating classes, for prediction, for creating topics, for a variety of things. Okay. Any questions so far? Please.
So if we have the higher mutual information with a higher number of classes, then the optimal mutual information would be when each word is in its own class.
Correct.
But that doesn't really tell us anything about the clustering, if every word is in its own class.
Right.
So in that case, would mutual information in general be the best measure of similarity or clustering or partitioning?
If you're looking for a measure of similarity, then I would look at the mutual information between successive words or merging words and rank them. I'm not sure I understand your question, but let me try to restate something else that might answer it, and if not, we'll come back to it. If your goal was to build a model that has the highest possible log likelihood of the training data, namely the lowest possible negative log likelihood of the training data, then the best model for that would be a pure word-based model, not a class-based model. Namely, every word is its own class. And when we derive this criterion, we're effectively doing that. We're saying, find the clustering that gives you the highest log likelihood of the training data. But of course, it's not what we want. We want the highest log likelihood of future data. And the distinction would come here. Instead of summing over the data, we would sum the log likelihood of a future data. So it would actually not be the entropy. It would be the cross entropy between the true distribution and our model distribution. You can do that if you leave some held out data. So if you make the clustering decisions based on held out data, then you can trust your clustering and you do not need to decide in advance the number of clusters. You could trust that we can set up the problem. In fact, let's do that. Let's write it on the board. If we want to maximize the negative average log likelihood of held out data, call it HO data, given your model, that would be the same as I don't have it here, I'll rewrite it. Negative 1 over, it won't be n now, let's say it's m, it's the size of your held out data. Sum of log p of word I given word I minus 1. In the limit, when m goes to infinity, this is the cross entropy. It's negative already, so it is cross entropy of from the true distribution to our model. I don't know if you remember, we discussed that when we discussed information theory. That sampling from the real world and evaluating by our model is an estimate that in the limit, when the sample goes to infinity, converges to, it's an estimate of what? It's an estimate of this. So it converges to this, which is the cross entropy from the true distribution to our model. So if you use this as your criterion for clustering, that is a safe criterion. It is not subject to overfitting. But
In this case, would more classes be better clustered?
not necessarily. It would find an intermediate number of clusters. Yes?
Instead of hard clustering, could you do soft clustering and, for example, assign a distribution over the vocabulary for each cluster?
Yes. So thanks for mentioning that. That's something else that I wanted to describe today. So soft clustering is a lot more complicated, but we can discuss two aspects of it. One is training such a model, namely deciding on the clusters, and the other is using such a model. So let's start with using this model because it's simpler. So another word for soft clustering is latent clustering, because the classes are now latent. Now I need to, it's not that classes are latent, I'm sorry, that's a wrong way of saying it. The classes are well known, they're not latent. What is latent is when you see the data, when you see the words, for any particular word token, for any particular occurrence of a word, which class represents it now is latent. You don't know that. So think of parts of speech as a classic example. We know what parts of speech are. We can write down the set of all prepositions, the set of all verbs, and so forth. But when a particular token like saw occurs, we don't know if it is now a noun or a verb. So in soft clustering, you have a vocabulary, and the classes now overlap each other. In the extreme case, every word can be in every cluster. But in the case of parts of speech, it's easier to think of this as partial clustering. The picture is still the same. I mean the graph. But now, when you see the words, so this is observed. And this is latent. So I shouldn't put the word here, because it's not the clustering that's latent, it's the stream of classes that is latent. This is the latent stream, this is the observed stream. Because it's latent, we need to take into account every value it could be. So if I want to write down the likelihood of this, just like there I wrote, when I wrote originally, I said that the probability of word I given word I minus 1, there I just broke it down as a sum over probability of a class given the previous the class times probability of a word given the class. Here I need to sum over all possibilities. So that would be sum over all possible classes of word I minus 1 and all possible classes of word I. And even that, so that's if I'm given everything up to here. If I'm told what's here and what's here, all right, let me change that. I'm slightly wrong. If I'm given everything up to here, I know what the class of word 1 is. I need to sum over only over all the classes of word that word 2 could be, right? So I know this. I know this and this, but I don't know the identity of this one. So it's class 2 that has to go everywhere from 1 to the number of classes. And now I have to write here the probability of class 2 given class 1, which I'm assuming I know, times the probability of word 2 given class 2. So instead of being a simple product of two terms, it is a product of two terms, but inside a summation over all possible classes. That's for figuring out just this, or rather just this, given that I already know this. If I now want to write down the likelihood of the entire sequence, I need to sum over all possible sequences of latent variables. We're going to discuss this in detail when we discuss hidden Markov models, but this is basically a hidden Markov model. Whereas the example we discussed the rest of class today is a non-hidden, a regular Markov model. The likelihood, the log likelihood of the entire data would be some, well, it couldn't be log likelihood like that. I'll have to write it as likelihood of the entire data. It would be sum over all possible class sequences from 1 to n. So there's a huge number of those. It's c to the power of n. Every possible combination of assignment of values to the latent stream of, now I can write it down as if I knew the classes. P of ci given ci minus 1 times p of word I given ci. So what I have here is a sum of c to the n different terms. Each one of them is a long string, a long product of, I'm sorry, I'm in a hurry, so I'm not thinking carefully. Now I have to do this. I goes from 1 to n, p of ci given ci minus 1 times p of wi given ci. This is the log likelihood of the entire sequence, entire training data or test data, given a particular assignment of labels to the latent variables. Given if somebody went and labeled every case, which part of speech it was. All this gets done multiple times for any particular assignment of the labels. So if two linguists looked at the same corpus and both labeled it differently, each one of them would correspond to a particular product here. And I need to look at all of them. That's only for, this is for estimating or for writing down the likelihood function given that you know what the model is, given that you know what this is. It doesn't answer the question of how do I cluster. So it's a lot more complicated. We can spend some time on it next time if you want. Use some other criteria for soft clustering. But just so you realize, this, even though it looks more complicated, it is computationally feasible. You can do it using dynamic programming. We will deal with that when we go to HMMs. The clustering question of how do you find good soft clusters is harder. And you do it all by heuristics. We meet again in 2 weeks, I guess, in Monday of. Have a wonderful break. Remind me to talk about mutual information versus correlation. And that's it. I'll see you then.